Could I invite our panelists to come up? That's Mark Kane, and Inez Fong, and Lisa Goddard, and Isaac Held, and George Philander, and Julius Lingo. And there's no place cards up here. I'm sorry about that. That's right, you're alphabetical. Yeah. Okay. All right, let me put this. All right, I guess Tom's controlling me here, so I won't touch that. We thought we would try something a little bit different for this part of the symposium. Rather than have prepared presentations on topics near and dear to each of the speakers, we thought we would pose a couple of questions. And I will admit up front that I think the questions aren't the best questions we might have asked. They were intended to be provocative, but I think we kind of missed the mark there. They are also intended to be forward-looking. I think we did okay there. But anyway, the questions that we posed to the panel in advance were these three. And they are sort of intended to talk about aspects of modeling and theory, observations, and education. So the first question is, how can we accelerate progress in accurately simulating current climate and constraining the sensitivity of Earth's climate to changes in forcing? This, of course, is a very important question that goes way out beyond our community of climate modeling, climate predictability, and climate dynamics, because it has implications for society, decision makers, risk assessment, attribution, treaties, et cetera, et cetera. Also, what are the prospects for a multinational dedicated climate modeling enterprise to reduce model bias, improve estimates of predictability, and bridge the gap between climate predictions and projections at the confidence scales? I put confident in quotation marks, thinking large scales are where we have the most confidence, and climate information at actionable scales, thinking that there is no government of the Earth to make decisions for the planet as a whole. And in fact, there's only one government of a continent, which is Australia. In general, the governments that we have that can make decisions are countries, states, counties, municipalities in the US, territories, provinces, et cetera, et cetera. So the decision-making that's done by governments is done at a scale that's far away from what I'll call the large or confident scales that we can make projections and predictions. So the question is, how do we bridge the gap and actually start providing information that's actionable? Second question we asked in advance was, how can we ensure that the necessary observing systems are maintained to provide complete and uninterrupted climate data? That, of course, is a question that one could have asked in the 1950s, in the 1960s, the 1970s. It's a perennial problem that we have, which is to say that climate, being a statistical problem, requires a lot of data, and it requires a long time series, and depending upon who you ask, the time series may be quite long in comparison with the actual record that you have. And furthermore, your observing systems are always changing. We're learning more about how to make observations. We're making investments in different ways to change our observing systems. So the question is, what is the best way to ensure that we get the observing system that we need to answer the important science and societal questions? And the third question we asked in advance was, because many of the people on the panel are educators, we asked, is the current educational system, either in the US or abroad, adequately preparing students to confront the big challenges in our field? And if not, of course that's a leading question, so if not, what new educational opportunities can be exploited to meet these challenges? So that was what we asked in advance. I also asked a few, I suggested a few examples in cover email to the panel just to kind of get their juices flowing, and I'm sure they have decided to flow in absolutely opposite directions from what I had thought of, so I'm really looking forward to what's about to come. The format will be, I'll ask each of the panelists to offer his or her reflections on these questions for about 5 minutes each. And then we'll open the floor for discussion and Q&A. And I have asked the climate dynamics students in the room to take notes. I've also, anyone else who would like to keep track of what's being said, because I'm going to be up here kind of herding the cats, so I won't have a chance to take notes. So I'm certainly happy if anybody has thoughts who would like to send those to me in the form of email either today or after the meeting. And the end result of all that is I do intend to produce a report. I don't have any idea where the report is going to end up. It probably will just end up going to NOAA that sponsored the project. But anyway, that is my sort of lofty ambition, is to try to prepare some kind of report out of this session. So if you have thoughts and notes that you'd like to share with me either now or in the near future, it's welcome. So. I guess what I will do is I will proceed from my right. Since Mark Kane, you were alphabetically first, we'll start with you, and 5 minutes.
Okay. I'm going to cede the floor to Inez.
Wait. This is not the Senate. This is not the Senate.
Can I have my slides, please?
Slides.
There's a conspiracy here.
Well, actually, it is a conspiracy in the sense of it, you know, there was about 5 minutes of preparation went into this.
Okay, that's fine.
I've copied the questions that Charlie put up. A meeting in 1955, the report is 1960, and that's the meeting after the first successful numerical weather forecast experiment on the ENIAC. That was 60 years ago. And in that, and this is with von Neumann and with Oppenheimer and Phillips and Lorenz and everybody, and in there are the questions that Charlie posed. And when you ask about big challenges, I'm looking at the questions again 60 years later and say how many of those have we addressed, how many of those have we solved, and I don't think we have closed the books on any one of them. So I'll start with the challenges. The second, while you're reading, so the celebration of Charlie's life that is now recorded in the book, edited by Linsen with AMS book, the science, Dick Linsen, chapter 12, Dick Linsen talks about the Charlie-Drazen theorem, but in it he talked about Charlie, the early life, when he said that after the ENIAC calculation, Charlie felt that he was becoming a propagandist. And of course this is Linsen, so you put your own weighting function on the comments. So that Charlie felt he was becoming a propagandist, and he was looking for other opportunities, and his move, he was contemplating, MIT was attractive because of Victor's star and the observations, and Lorenz had just done what Lorenz thinks is his best work, which is the available potential energy. So that's my start, is looking at the challenges. I'm looking at the challenges laid down 60 years ago and wondering where we're going. Okay, so you want to comment before I go? Yeah. Okay. So I'm a dutiful student. So here the next slide are answering one of your questions, the California drought and food security. And what you see is the agricultural water. This is in the drought, the wasted water. This is runoff from the agricultural fields. Next one, please. And so California water, and just in case you don't know, California supplies 45% of the fruits and nuts, that's where we are, fruits and nuts here, and vegetables in the US, and you can see most of the produce. Next one, please. But what we see what we consume in the U.S. is only part of what California produces, and so alfalfa 17% is exported, but almonds prices going up here, with 70% of the almonds produced shipped overseas, etc. So I'm looking at California drought as an issue of food security. California is exporting cheap water to overseas while the governor is telling us to take shorter showers. So here's a metric. So the alfalfa goes into dairy cattle, and you can see the numbers. So vegetarians can take a longer shower than carnivores. Okay, so I've been trying to figure this out. So 80% of the freshwater use in California is for agriculture. So as I said, much of it is exported overseas. Next one, please. The more important thing here is that the rainfall is, the agriculture is supported by groundwater, fossil water, if you will, not current rainwater. Next one, please. And so the challenges, when I look at California drought, one of the scientific challenge is the atmospheric river, which supplies about 50% of the rain in California. So it's a modeling challenge, it's a physics challenge, sometimes called the Pineapple Express. And there's stories of Governor Leland Stanford rowing his boat to his inauguration as the governor of California a long time ago, etc. So that's an outstanding atmospheric science question. Is an outstanding model question. If you give it the conditions, you can get it, but you can't generate one. So where's the landfall, etc. So the next one, the challenge for California drought, for me, is understanding groundwater. That's something that we're not doing in the models. At least I'll speak for the NCAR model, we have a concrete floor at 3.8 meters or 3.4 meters, and so there's not much information. And so groundwater, obviously, the supply for groundwater would change with decreasing snow melt, and if we have intense precipitation, the portion that goes into runoff versus infiltration in the groundwater, it's likely to change. And so that's a question, again, that I think is a challenge we have to think about when we think about not just the science part of it, but the science for what society needs. But the last one I can't handle because conservation is good, taking shorter showers is good, but since 80% of the California water is in agriculture, there has to be a reform in the agricultural, in the economic sector, and that's beyond my capability, so I'll stop there.
Great, thank you. Mark?
Well, switching gears, I think, the first, about 11,000 years ago, the world was almost as warm, about as warm as it is, well, 200 years ago. And in about 10 years, it dropped 2/3 of the way into an ice age. Now, we don't understand how that happens, or at least I don't, and if somebody else does, that would be good. This kind of bothers me because while the world then was quite different, and there was a lot of ice around, and I don't think exactly whatever happened then is what might happen now in terms of some abrupt climate change, it does seem to me troubling that we don't have a reasonable explanation of how this is possible. Okay. And I think at one point you might have dismissed the paleoproxy evidence as coming from one source, which is a little funny, being polar ice caps. But you see the same thing in speleothems in China and other places. So I think it's pretty likely that something fairly extreme did happen. And it seems to me that some greater attention to, what these, okay, maybe it's an outlier, but it would be rather difficult for society to adjust if we had a similarly abrupt change now. That's one thing. Second thing is an answer to many of the questions. Don't put them back. Please. I think that one of the things we do, well, an awful lot of resources and attention have gone somewhat properly into projecting the future. And this would be okay, except that very often this is done without checking to see if models actually reproduce the records that we are aware of, the observational records we are aware of. And that's a rather bad tendency. It's nice in a way to focus on the future because there's no way to check it, for a while anyway. And many of us looking around who are contemporaries of Shukla won't be here to check it. So, you know, that's kind of safe for us. But I think, you know, for example, we've just done some work on rainfall in East Africa. You look at the models they project with global warming that it will get wetter in East Africa. You look at what's happened in the last 10 years. There's been a horrific drought. The drought has been a failure of the long rains in this part of the world. There were short rains in the fall, long rains in the spring. Okay. You look further into the models, you discover that they don't get the climatology right. That is, they have their long rains in the fall and their short rains in the spring. So, yet there was an awful lot of projections built on what models projected for the future for this area, and it has, you know, great humanitarian implications. And it's obviously, if you just go back and you check what it does, what these models do for the 20th century, it should be fairly obvious that this is all nonsense. But I think not enough of that kind of work has been done. And if we want to actually grapple with questions of what, you know, how to make the models better and answer the Charney questions that are still unanswered, then I think it would do us well to focus more on what has happened and try to get that right first.
Great, thank you very much. Lisa.
Well, the bar has been set pretty high now. So I want to follow on to some of the comments that Mark was making, because I agree very much with the sentiments that there's both good and bad in what's been going on with the IPCC and CMIP. The unfortunate thing is that this process has just become incredibly politicized, which has then set a lot of people very hard-lined against considering it all or investing in it. And also the difficulty in getting countries to coordinate their research on it. So, you know, in the interest of international and maybe making progress on these huge problems that have been out there for 60 years, there's still this real challenge in getting countries to come together with substantial, enduring funds to tackle these problems. I mean, these are not things that can get done in a couple years. They're not things that are going to be done by a single country, and so to the extent that there's duplication or there is just a frustration in being able to collaborate because of the difficulty in getting teams that can work across countries. The WCRP has been fantastic in coordinating these things, and I think that there have been interests in, so CMIP, for example, from the World Climate Research Program, has been a fundamental change in our way to work together on common organized data sets about the current climate, which I agree are underutilized, and the future climate. But really having the resources to dig into dealing with these huge biases and questions and processes that still exist in the models, I think that's just an agreement that needs to occur between countries that are invested in that to bring people together to work on it. I think my own opinion is things like the Belmont Forum are not working well in that direction. But back to the politicization of CMIP and the IPCC, What's unfortunate about that is I think that there's so much climate information that could benefit communities and governments and businesses, and if that information were provided for the purposes of those decisions and that use across timescales, then it's much more likely that people would be open to the value of the models and the observations and thinking about how to incorporate these into decision making. Instead, there's so much hardline now against actually using everything in many countries, including the US, climate equals climate change, and that's not really the case. So people become very tunnel visioned on climate change. So things like the East African drought, for example, maybe even the California drought is convolved with climate variability and climate change. Everything becomes climate change in the mind of the public because the scientific community has been so successful in their message of the importance and the potential devastating impacts of climate change that when any sort of devastating impact comes down now, it's interpreted as climate change because there's probably a model out there somewhere that has that impact. So it's really important to be able to, this is another research challenge, to be able to distinguish the processes that are driving climate variability, climate change, the possible interaction between those things. And then once you get down to the, what Jim calls the actionable scale, more regional to local scale information, that's yet another challenge. I think that the downscaling efforts of these models is not going in the right direction. I see quite consistently that the information that those models are supposed to be providing, which is the response to increasing greenhouse gases, is believed, and the only thing that's missing is spatial and temporal scale. And that's a problem. So what you want to know is not, does the model have the right climatology of extreme events, and so we should believe what it's saying about the future climatology. We want to know if those models have the right response to changes in extreme events, and for example. But those sort of things are really not being looked at. And I'm going to jump to the third question because I think it's related to all of these things. Having good science and good models, it doesn't get that final mile that Julia was talking about yesterday. This really requires a whole army of experts to bring this information into reasonable use. And so, current educational system, I mean, that can range all the way from kindergarten up to college, and I'm not sure what Jim was indicating. I know that I have some definite frustrations with the math system in my kids' schools. But let me focus on the colleges right now. I think that there's a debate in the community about the value of multidisciplinary research versus transdisciplinary research. And my definition, just to clarify, multidisciplinary, I would say, is taking a collection of people that are experts in their discipline and having them work together. Transdisciplinary would be putting all of those disciplines in a single individual and having them work on a complex problem. I am a huge proponent for the first one. I think that there is a lot of debate in there, so this is very much my own opinion. So in the sense that the universities are still very disciplinary, I think that they are doing well in producing people that are strong in physics and math and chemistry and anthropology and economics in those fields. Where I think that the universities are falling short on allowing us to address these complex problems is in that multidisciplinary space, providing it and supporting it. So for researchers that go into multidisciplinary research, there's not a reward system. It's very difficult to have sustainable research programs, etc. And I think that sort of, those sorts of programs can be brought into student settings as well. We know that especially for really bright people, the real world is a great laboratory. And so having opportunities for people, students even, in their disciplines to come together to work on challenging problems, I think would be a great opportunity. But I would not advocate for the direction that some programs seem to be taking, that is trying to merge many disciplines into one individual, because I think that results in a broad but more shallow expert for the future.
Great. Thank you. Isaac.
Surprise me.
Oh, sorry. You're next alphabetically.
Yeah, perhaps I can provide a little counterpoint to the natural emphasis at this meeting on prediction and predictability and seamless modeling. Obviously, we're all talking about the same physical system, and the natural way to go is to have everyone working together on the same modeling system. But as the first question implied, and also the reference to Charney's questions, I'm also dissatisfied with the rate of progress in improving our simulations of climate, and curious about how to accelerate it. And I'm not patient enough, personally, to wait for the prediction world to gradually improve their medium range forecasts, and then their seasonal forecasts, and then their decadal forecasts on longer and longer time scales, waiting for the requisite time to get enough events to test one's prediction systems, and then eventually moving to the centennial scale, which is sort of the most relevant scale for the anthropogenic warming pulse that many of us are so concerned about. And so I'm reminded of one of my favorite poems. It's by Andrew Marvell, To His Coy Mistress, and you have to substitute the climate system for the mistress of this poem. I won't do that explicitly. The first line in the poem is, "Had we world enough and time, this coyness lady were no crime." If we had all the time in the world, sure, that's the logical way to proceed. You validate what you're doing, you convince yourself and convince the world that your model is good by actually doing predictions. That's obviously the ultimate test. But we just don't have that much time. Marvell goes on, for example, to talk about if he did have time, 100 years you go to praise thine eyes and on thy forehead gaze, which sort of reminds me of some of the things we obsess about, trying to, here's a little something, maybe it's not so little, but doesn't look very good in our models. We can't predict the climate until we improve it. But there are thousands of things like that, literally thousands of things you can point to. And how do you have to prioritize. I won't go on to the other things he categorizes about his mistress, which are inappropriate. But near the end, then he comes back to time's winged chariot turning near. I think a lot of us feel the urgency of improving our projections of climate change, our risk assessment. And the key to that, I think, is trying to determine through creativity and thinking about how the system works, about what are the priorities, what things do we really have to simulate that really matter for these projections. And I don't have to talk, a lot of people in the audience have written about this. I mean, Shukla and Tim Dalsell talked about simulating the seasonal cycle, a nice paper a number of years ago. They thought and provided some arguments. That's the starting point. That's the key. It's a forced response after all. I like that. But there else. I think I will propose something here that I don't really have the answer to, but I think that's the key. Prioritizing one way or the other. What are the key things that we have to simulate and that we potentially can constrain with observations? And I think from the point of view of the climate change problem, that should guide our observational strategy. You have to decide first. I mean, you can decide to observe everything, but more practically, if you have some agreement in the community that these are the things that we really have to model properly and we have to observe to test our models, that would be much more efficient. So that's the struggle. And I liked Mark's comments on attribution effectively. I think you can think about climate projections as sort of, I think there's sort of a two-part problem. The first part, sort of zeroth order approximation, is extrapolate your attributed force response. So attribution in the forced climate change problem is prediction. You take the attributed force response that you attribute to CO2 and you extrapolate it into the future. So some people call that linear assumption. You say it's extrapolating something that we see happening, but the key is to be able to do a convincing job at attribution, whether it's California drought or East African rainfall. If you can't do the attribution, then there's nothing to extrapolate. And then the second half of it is, well, to do better than extrapolation, which I think the bottom line is risk assessment, as Lynn already said. What are the places where we might really be surprised by the system? And can we isolate some sources of potential surprise and really focus on those as research problems? That's pretty vague, but going into education, if I still have a minute.
Sure, go ahead.
Something else I worry about a lot in that, but I focus a little bit different from Lisa's. I'm concerned about attracting the best students in, say, science, physics, computer science to our field. There are a lot of really bright students out there that go into other things for all sorts of reasons, but how do we attract more of them? It's not that we don't get some of them. I'm sure some of them are sitting in the audience, but we need more, and how do we do that? And I just come to the conclusion over the years, you don't do that by trying to attract students to work with your comprehensive modeling systems. It's just on the educational timescale, it's just not possible to master those models well enough to work with them really, let's say, creatively. Not that there's a lot of important things going on. Of course, there are a lot of things people do manipulate the models, but to take a comprehensive model seriously as a dynamical system and think about it as a theoretical physics, theoretically oriented student who would like to do that, it's almost impossible, I think. And the models also become obsolete as computers progress. So after 5 or 10 years, you spent years studying a particular system, and then 10 years from now, people aren't interested in it anymore. What was the point of that? Hopefully we've learned something about the climate system. It's not that we've learned something about the model. Hopefully we've learned something about the climate system. So I've been pushing the idea of trying to construct models that don't become obsolete. We have to agree on somehow, as a community, on a hierarchy of models, or whatever you want to call it. But there are models that are sufficiently interesting that even with computer power increasing over time and observational systems improving, it's important to understand these dynamical systems. They're a part, we agree that they're a part of the core complexity of the climate system that we want to understand. And I think educationally, I think it sometimes works that the really best students are attracted to that kind of problem, where they're working on something a little bit more manageable and doesn't become obsolete over time.
Thank you. George.
Yeah, I'll comment on 1 and 3 and skip 2.
Okay.
I echo Isaac's sentiments concerning the smooth transition from weather to climate. And I think it's feasible. Our big success has been weather prediction. And yesterday Leonard spoke quantifying how successful it has been. And I want to give a historical perspective of why has weather prediction succeeded. And any science is an interplay between measurements and theory. And we usually have 2 complementary approaches. The one I will call holistic. If you ask me, why do the continents drift? then I will show you a host of different reasons. The shape of the continents are matching. Wegener proposed that, and nobody really believed him. So I had to come up with more evidence. You look at the magnetic field of the seafloor, and the age of the seafloor, and fossils, and so on. In the end, it's a sum of a huge number of factors, and any one of them you could discard, and you would still believe. The opposite way to proceed is a reductionist way. And if you ask Newton what determines the trajectory of a planet around the sun, he writes down some equation that has a magical term, gravity force acting at a distance. Nobody believed that at the time, but the results were so spectacularly in agreement with measurements that people accepted Newton. And so what's intriguing, Newton's approach brought him fame in his lifetime. And Wegener had to wait quite a while for his recognition. The success of weather prediction, I submit, is a marriage of these two approaches. So up to World War II, weather prediction was realistic. Very complicated maps and the rules of thumb as to how we're low and high, warm front and a cold front behave and so on. Then the invention of the computer brought about a radically different approach to weather prediction, a reductionist approach. And I would argue yesterday, we will have to come back to discussion, the need for bigger computers and so on. I would argue the people in the 1950s had the advantage of very weak computers. And so the reductionists ask questions such as why is there weather? Things like baroclinicity, instability, and how long can you predict it with Lorenz's? And those didn't require big computers. The two approaches are so different that one proponent of the reductionist approach, Magrinsky, moved away from the Weather Service to Princeton, New Jersey. Which is an indication of how difficult it is for these two groups to communicate. Finally, weather prediction is so successful that the models are tuned on the basis of measurements. But if there is an errant measurement, the models can actually tell you which are the errant measurements. So it's an absolutely beautiful marriage of reductionist and holistic approaches. If we turn to climate, we immediately run into the serious problem that we have very little data, nothing compared to weather. And I would submit that the climate hasn't really changed in the last 1,000 years. So we're really obliged to look at paleoclimates. There are huge signals there. If you ask climate models what have they focused on in getting the climate of today right, I would argue the climatological seasonal cycle. And it's a recurrent signal. And we still have many unanswered questions concerning this particular signal. Shukla has pointed this out. So I would argue that our hope is to look at the recurrent signals in the past, things such as ice ages. They recur, and what's astonishing is the people who study that take a very holistic approach. They tell you stories about things that happen, and progress there is measured in how much more detail they can give you. Nobody has asked what is the simplest world in which you could have ice age. If the Earth's orbit was a circle, could you have one? If there was no molecular forcing, could you have one? So there's a wide open field, I feel, in the study of paleoclimates that has not been exploited by the people on the reductionist side. It's actually, I've tried the last few years to bridge this gap. There's some problems I'm interested in that cannot be tested. Some ideas for different types of El Nino. The only solution really is in the paleo. And I assure you it's extremely, this marriage between reductionist and holistic is a very difficult one. Most people will, marriages are complicated institutions, and most people will deny there's a problem. I was going to ask Mark Kane at Lamont, they have both the reductionists and the holistic people. How are their conversations coming along? We can get back to that later. Anyway, so I think that the whole field of climate prediction is basically where weather prediction was in the 50s. It's at a very exciting stage. There's a quote from Worston who says that the biggest impediment to progress is not ignorance, but the illusion of knowledge. And I think that's sort of a big handicap in this. There are just too many people who know, or think they know about things like I said. Just anyway, we can discuss that later. Let me just jump to the third one. I have 2 points to make to the third question. One is a story for Eugenia, and it's a story about Isaac Newton. And Isaac Newton at the time was a famous man, and there was a company that brought goodies from the South Seas, the South Pacific, to England. They wanted to build more ships to bring more goods. And the stock of this company was going up and up. And Newton bought some of the stock. And he got suspicious that it was increasing so rapidly. He looked into the matter and called a press conference and announced to the world that he was selling his stock because it was a big fraud, that this company wasn't actually doing anything concrete. This news conference had zero impact. The prices of the stock went up and up. Then a few weeks later, something astonishing happened. Newton changed his mind and bought more stock in the company. And then shortly afterwards, the thing collapsed. It was called the South Sea Bubble. And Newton made the statement that I can predict the motion of heavenly bodies, but not the madness of men. So anybody who tries to write down equations that will tell us how people behave or should behave should read Bernanke's the Fed. Anyway, the fellow who was in charge of economy in 2007 written a book about what happened. What's most astonishing, they had not the foggiest idea what was going on, nor the foggiest idea what to do. So anyway, I'm very suspicious of any attempts to treat human behavior as if it was a scientific problem. We could write down equations and solve it. My other comment on how we attract students, I would argue that everybody in this room agrees that global warming is a serious problem. We should do something about it. If we have a wider poll, if we ask the people in this hotel how they feel, it will turn out only 50% share our beliefs. And in general, if you look around the US, we've completely failed to persuade half the people. So global warming is extremely polarized. The two proponents, the convenient one says Al Gore is one, and Michael Crichton is the other. And it's quite fascinating that these two very responsible people, Crichton died a while ago, should have highly intelligent, responsible people. How can they disagree on something as important as the future of planet Earth? And what's intriguing, everybody has seen Gore's movie. Crichton has written a book called State of Fear. And it is not worth reading. You could turn to the appendix. But what I found intriguing is the appendix explains why he's skeptical of global warming, and these reasons are mostly political. But I'm intrigued by his title, State of Fear. And I think we should take a lesson from this title. I think we're using the wrong strategy in trying to persuade the public. And I came to this conclusion after spending some time in Africa. And what I learned there is we're all about doom and doom. And you cannot tell poor people, people who don't know where the next meal is coming from, you cannot tell them that the future is going to be worse. You really are obliged to give them hope, tell the future will be better. And so I propose that instead of emphasizing doom and doom, we try to make people aware of what an astonishing planet this is. NASA gets lots of publicity for finding that there are billions of suns, and each of them has planets, and so billions upon billions of planets. Precisely one is known to be habitable. It's this one. And we've failed, and we should take a lesson from people in public health. Everybody here and outside this room knows about the heart, the lungs, the liver, about hygiene, washing your hands, diet. I submit that nobody outside this room has the slightest idea why this planet is habitable. And it's really our failure. So, like Isaac went, if we want to attract students, I think we'll be far more successful with presenting this puzzle to them. Why is this a habitable planet? And we experience a big annual climate change global, everybody's aware of. It's the seasonal cycle. So this will come back towards if we want to develop models, if we want to inspire people. I think we're likely to have more success by paying attention to such obvious phenomena.
Thanks, George. Julia.
Right, I'm going to be very brief because you had to listen to me rather longer than 20 minutes yesterday, for which I apologise. and I think I said yesterday I addressed quite a few of these issues in what I said yesterday. So, for sure, we have to improve our models. At the end of the day, they are our laboratory, and it's the way in which we use them to understand how the system works and how it responds to different forcings. We shouldn't forget that a computational laboratory is we want the best we can get our hands on, which is why I and many of us in the room have always fought for larger supercomputers and better models, higher resolution. I think the case for more resolution is just patently clear. What's really exciting, as I said yesterday, is this ability now to model down at the kilometre or even the sub-kilometre scale. And if we want to tackle convection, which I think still arguably is the most important process in the climate system that we haven't really been able to get to grips with, we now can do that through these computational laboratories, and we need the best brains around to help us do that. This is a really, really big problem. So I'm positive. I think we're going into a golden age in a sense of atmospheric physics, because we can actually now model at the scales at which we observe from satellites, from aircraft, in situ and so forth. Do we have the observing systems we need? Well, of course not. And I think when we think about where does all the heat go, I think the big gap in knowledge is still where does all the heat go in the ocean. Not to be able to answer questions around decadal variability, multi-decadal variability of the climate system, how that happens, and what the prospects are for that in the coming, say, 5, 10, 15 years, just shows how young our science is. And we need to think about other methods of observing the planet beyond always from space, because that can't tell us everything that we need to know. Finally, just something on education. Tim has started a very interesting little email dialogue on this in the UK with a few colleagues abroad, and it's something that I think about quite a lot from the perspective of the Met Office, who's you could argue, a major employer of scientists in this field. And do we really attract the best physics, maths, chemists, best scientists into the field? And the answer is probably not. And what can we do about it? I don't have an answer except to think that, well, at least in the UK, we've started something called the Met Office Academic Partnership with 4 of the major leading universities. And there are some mechanisms you can employ which don't cost very much money that raise the profile of our science at the undergraduate, I would argue, and at the graduate level. And these are things like industrial scholarships in the old ways of forming a relationship with an undergraduate at a very early stage, exposing them, if they're good, doing physics and maths degrees, exposing them on a regular basis to our science. We give undergraduate prizes. They don't cost very much, but they're always elevating the importance of the science we do. We offer partnerships, PhD studentship partnerships and things like that, joint supervision. So I think the big institutions like ourselves can play a really critical role in actually encouraging good physics, maths undergraduates into our subject. So I think this is something that we as a community need to think about. Tim has started that discussion. I'm sure he'll comment on this when we open it to the floor. So I'm going to stop there. I said enough yesterday. And happy to answer questions.
Wonderful.